Hello. In this particular lecture we are going to discuss about the thin film for surface engineering of nanomaterials. So, in last couple of lectures we have discussed about some kind of problems on based of wear, then abrasions, then we are trying to modify those problems, then we have discussed about several types of deposition techniques, then we have discussed about the modifications of nanomaterials. So, in this particular lecture we are going to discuss about the thin films, how it is helping for doing the surface modifications of particular materials. So, here first before going to start, let us know that what is the definitions of the thin films. So, at the onset let me discuss that thin films is very difficult to define, because some people thinks that 300 nanometer is the thin, some people are thinking that 2 nanometer is also the thin. So, the thing is that it depends upon the applications, that what are the applications of that particular materials, based on that we can define that materials whether it is thin or maybe the thick, because I will give you some examples where you can find that in nanometer range also there is some kind of materials which can act as a thick. So, thin film is a layer of substrate or materials on supporting substrate ranging from nanometers to several micrometers in thickness. So, as I already told, maybe that size maybe in the nanometer range, maybe sometimes it is in the micrometer range also. So, distinction thin film or maybe the thick film, the limit between thin and thick films cannot generally be defined, because it is very difficult to say, although literature sometimes gives an arbitrary value of 1 micrometer. Basically a film can be considered as thin when its properties are significantly different from the bulk. Yes, of course, because in the subsequent slide we will see that when we are making that thin film, it is giving the better properties in terms of electrical, in terms of mechanical, in terms of thermal than the bulk or maybe the thick film. So, for example, an indium oxide films which can be used as a temperature barrier, this one is the material coating due to its high transmissions in the visible regions and its high reflectability in the infrared region. This is caused by optical interference effects, has to be approx 300 nanometer thick. So, you can imagine that here 300 nanometer we are considering as a thin materials. For optical applications this film can be considered as thin, but when we are talking about particular these applications, that 300 nanometer we are considering as a thin material. If the same material would serve as insulator in a Josephson junction, 300 nanometer would be much too thick to allow Cooper pairs. Cooper pairs is nothing but the materials which we are using in between the two semiconducting layers. So, through the oxide for these applications the indium oxide film should have a thickness of only 2 nanometer. So, now my one basic question is that whether we are going to say that 2 nanometer as a thin or thick, or maybe the which one is the thicker or maybe which one is the thinner, whether 300 nanometers or maybe the 2 nanometer. Here are the answers. In other words, for one given applications a thin film can be considered as thin, while for another applications the same film can be known as a thick. So, it depends upon application to applications, somehow somewhere one film can be used as a thick, somehow the same dimensions can be used as a thin. Classification of thin films on the basis of crystalline structure. So, generally we can divide the thin films into 4 classical divisions. One is called the single crystals, epitaxials, amorphous and the polycrystalline. So, effects of thin films. So, just in this particular slide I am going to discuss about the, if we are going to use those kind of thin films, what are the advantages we are going to get. So, a microstructure which is different from the bulk, that means in respect to grain or crystallite size, the following effects may be observed: increase the corrosion resistance, improve hardness, enhance magnetic saturation inductions, which is nothing we are getting from this particular graph. In the right hand side it is giving the saturation magnetizations which is into the x axis, which is into the y axis, and the x axis is giving you the temperature. So, from this particular case you can see that when our thin film thickness is only around 2.1 nanometer, it is giving the saturated magnetizations value as around 600. So, when we are using our materials as a thin, the properties is getting increased. So, what it is doing? It is increasing corrosion resistance, improve hardness, increase critical temperature of superconductivity, amplify the optical absorption. So, if we use the thin film, then it can enhance so many properties than the thick film itself. Now, let us discuss about the history behind this. When people have started, generally roughly people have started using this kind of techniques in the year of 1650. So, from 1650 to 1940, observations and interpretation of interference patterns, development of fast deposition techniques, thickness determinations, coating for optical, electronic and mechanical applications, people were working on these kind of things. From 1965 to 2004, use of thin film technology in semiconductor and optical industries, manufacturing of nanocrystalline materials with defined compositions and structure for applications as protective coatings, and in tribology people were working on these, and now people are working on these all kind of advanced materials from 2006 to till date. Investigation of organic coatings led to emergence of organic electronics, OLED, printable circuits, dye synthesized solar cells, quantum dot solar cells, peroxide solar materials and so on. So, how we are doing this thin films, or maybe rather we can say how we are preparing these thin films, what is the growth mechanisms over there. The deposition process of a film can be divided into three basic phases. So, first one is called the production of the appropriate atomic, molecular or ionic species. So, this one is the number one methods. Then second is that transport of these species to the substrate through a medium. So, this is the second one, and last one is the condensation on the substrate either directly or via a chemical or electrochemical reactions to form a solid deposit over there. So, here this is the gas flow is going on, then the atom is coming, first absorption on film precursor it is taking place, then nucleation of these atoms is taking place, and the last one is that step flow growth, means layer by layer it is forming and it is giving a coating onto the material surface. So, some particular motifs of thin film depositions, what are the logic that why we are going to use this kind of thin films for surface engineering. So, first is that to maintain the surface uniformity. So, we can get a homogeneous surface structure over there, smoothness of the surface will be good. To reduce the amount or mass of light absorbing materials, to decrease the weight and bulkiness of the materials. That means, we are reducing the weight, we are reducing the volume, but simultaneously we are enhancing the properties than the bulk film or maybe the thick film. Growth of a thin film generally exhibit following features. The origin of thin films on all materials created by any deposition technique starts with a random nucleation process followed by nucleation and growth stages. Nucleation and growth stages are dependent upon various deposition conditions such as growth temperature, growth rate, substrate chemistry. So, the thing is that it depends upon our requirement, that how many layer we are going to make onto the substrate, what is the substrate conditions, how much temperature can sustain this substrate and the thin films. So, it depends upon what property we are going to achieve. So, depending upon that we can go for a single layer, we can go for a multiple layer deposition onto our substrate. So, what are the techniques for deposition of thin films? Generally it can be divided into two parts, one is called the gas phase, another one is called the liquid phase. Gas phase, generally we are discussing about the PVD process, physical vapor deposition process, and the CVD is called the chemical vapor deposition process. If you remember, we have discussed this PVD process and our CVD process in details in our lecture number 12 and lecture number 13, and in this particular slide we are going to discuss about this kind of things into details, that is called the liquid phase, which is divided into four parts. One is called the electroplating, then spin coating, spray pyrolysis and the deep coating techniques. Now, in a single or maybe brief manner I am going to discuss about the gas phase deposition techniques, which is the first one is called the physical vapor depositions. The word physical distinct from chemical is intended to indicate the absence of any chemical reactions in the formation of the films. Generally it is abbreviated as PVD. Simple, we are having that precursor, we are heating that material, we are making any kind of gas or molecules, and then directly that gas and molecules is coming onto the substrate. There is no chemical reactions in between that coatings and the substrate. So, that is in general says is called the physical vapor deposition techniques. Next, The chemical vapor deposition techniques also we have discussed in our earlier slides. So, the chemical vapor deposition is that same thing, like that we are introducing some kind of molecules, ions, some kind of plasmas, but those materials can react with the substrates, they can form a new species, and like this way they can do the coatings onto the substrate material. So, here the difference between the PVD and CVD we have shown over there. Then some cases we are getting some good properties, some cases we are getting the some bad properties, or maybe the better than the PVD methods. So, it actually depends that what kind of substrate you are going to use. Depending upon that, you have to choose that whether you will go for the PVD method or maybe you will go for the CVD methods. So, now we are going to discuss in details about the liquid phase deposition techniques. Okay. So, first one is called the electroplating. So, an electrochemical process where metal ions are transferred from a solutions and deposited as a thin layer onto a surface of a cathode. So, from this particular figure you can understand that we are having one cathode, we are having one anode, and then we are using certain kind of potential difference in between that. So, that metal ions is coming, we are using some kind of electrolyte solutions over there, then some kind of plating is taking place electronically. So, what are the advantages? Low temperature treatment applicable to metal substrate, disadvantages not applicable to insulating materials, poor thickness uniformity, that means we need some kind of conducting materials for doing this kind of modifications. Next one is called the spin coating process. So, in this process liquid precursor is deposited onto a smooth and flat substrate which is subsequently spun at a high speed to centrifugally spread the solutions over the substrate. So, here is the positions. By drop casting methods we are putting a droplet onto that particular surface, then we are rotating that disc in a very high RPM, and due to the centrifugal force this material is spread all over around this disc, then we are drying that material and we are taking out that material, and that is known as a thin film depositions by the spin coating process. So, what are the advantages? Production of uniform film, low temperature depositions, disadvantage difficulty with the large area, because we are putting certain kind of droplets, sometimes it can't cover the whole disc area at a time. Then next one we are discussing about the spray pyrolysis depositions. Here it is nothing, it is a simple like the paint when we are doing onto our automotive parts or maybe the wall or some kind of spray painting we are doing. So, it is a process in which a thin film is deposited by spraying a solutions on a heated surface where the constituents react to form a chemical compound. So, what are the advantages? Coating of materials and insulators, cost effectiveness, deposition of large area, major disadvantage, difficulties with growth temperature determinations. So, from this particular figure you can understand that we are having some kind of spray gun. So, directly some kind of carrier gas it is coming over there, we can regulate this pressure of this particular gas. Then we are having some reservoir, that means which materials we are going to coat onto that materials, that reservoir we are putting over there. Then we are having a spray nozzle or maybe some kind we are calling it as a gun. In that gun we are having that facility that these precursor materials and this compressed air can be mixed properly, and then that can be thrown onto the substrate itself, and the substrate is kept on some heater so that we can increase or decrease the temperature of that particular substrate. So, we have to heat that substrate so that when that precursor with the gas molecules it will directly come into the contact with the substrate, they will make certain kind of chemical bonding and the material will be agitated and they will form a new material, so that we can get a film onto the top of the substrate. Next is called the deep coating. It is a process where the substrate to be coated is immersed in a liquid and then withdrawn the speed under controlled temperature and atmospheric conditions. So, simply we are dipping that material into that solutions and then we are taking it out. So, what are the advantages? It is very low cost, low processing temperature, but it is the poor additions because we are not using any kind of temperature over there. Simply we are dipping our substrate materials into some solutions and we are taking it out and then we are drying and we are using those materials. So, what are the applications of that thin film technology? Engineering processing, generally we are using for these materials for the hard coatings for cutting tools. So, generally we can do the coatings only the cutting regions, so that the tool will be inexpensive. Not only that, sometimes we can change the cutting geometry of this particular tool by using different types of inserts, that inserts can be made by different types of coating techniques. Then protection against high temperature corrosions. So, generally for the chimney or maybe some kind of exhaust pipe, we can use this kind of coatings where the flue gases is directly coming, it is getting the contact with the material or maybe the substrate, it can harm that material. So, that we are doing certain kind of coatings, so that that flue gases or maybe the toxic gases not directly come with the contact with that particular material. Then we are using these materials for the catalyzing coatings, for some decorative things, then some tribological applications, protective coatings to reduce the wear, corrosion and erosions, any kind of vehicles or maybe some kind of aeroplanes or maybe the any kind of submarines, ships, where that materials is going into the water or maybe that materials is going into the sky, so that there will not be any corrosions, there will not be any scratch on that particular material. So, for optics also we are using this kind of coatings for the anti-reflex coatings. So, right side is the anti-reflection coatings, you can see the changing into the color itself, but both are the transparent, but the difference in between that, the light can pass through by this lenses, but here the light will be reflected. That is a very good for using this kind of glasses while we are using some kind of computers, while we are driving our cars, so that the opposite side headlight not directly come into our eyes. Some interference filter also. So, we can use that certain materials or maybe that certain light, it can pass through these materials and certain light can be reflected by this material, so that we can segregate the different frequency of that particular light. Then we can use it for the beam splitter and thin film polarizing materials, and the best application is that we can use this kind of coatings or maybe the thin film technology for the electronic purpose, generally for the printed circuit boards. So, nowadays we are using this type of materials for our tablets, for our mobiles or maybe for our computers or maybe the laptops. Then we are using this kind of thin films for the solar collectors, solar panels, solar cells. Here you can see that there are several layers by which we are making the solar cells to increase the efficiency of that particular materials. We are using this kind of materials for the lithium ion battery. Not only that, we are using this kind of materials for the gas sensors and the humidity sensors, which can detect the humidity of that particular room, which can detect the toxic gas are present in that particular room or that particular area or not. So, and not only that we can use these materials for the energy harvesting applications, we can use these materials for the energy storage applications. So, there are lots of applications where we can use this kind of thin film technology. So, now in summary we are going to discuss that what we have learned from this particular lecture. So, discussed various stages in thin films development from historical perspectives. There are various thin film fabrication techniques including PVD, CVD, spin coating, electrospinning and so on. We have already discussed all those things in details in our earlier slides. Thin films have been extensively recognized for a wide range of potential applications such as electronic, optical, sensor, solar cell, battery, but again I am telling the same thing, these applications are very few, there are numerous applications where we can use this kind of thin film technology. So, potential of thin films for future usage, developing molecules out of organic compounds like carbon and hydrogen. Super thin film about 100 nanometer thick can be applied as paint, replace heavy metals currently being used in cells, create biodegradable natural cell. So, these all are the future applications of the thin films. Still the scientists and researchers all over the world, they are working for preparing different types of thin films for numerous applications. Thank you.